Thank you, Megan. Appreciate it. Yeah, I thought it was timely to focus in on how LANDFIRE uses image-based machine learning modeling to map vegetation and update fuels. It's an important part of what makes LANDFIRE valuable and unique, how we do what we do. It's what I know most about, so that's why I picked this topic to talk about today. So here are all of the LANDFIRE products. As you can see, there's a lot of them. They're not, and what we're going to be focused in on today are these vegetation products, cover, height, and type, which uses the ecological systems classification, and this forms the building blocks for fuels products and fire regime. So although we have, a lot of products, and don't think that they're independent or separate, because there's a lot of interconnections. The reference and disturbance products are used to build the vegetation products, which then are in part used to build the fuels and fire regime products, as I mentioned. So I just wanted to give an overview of LANDFIRE and then what we're going to be looking at today, but also that there are important connections. It might seem like we're just trying to map vegetation correctly, but really what this is looking at is how we map current ground conditions that feeds into getting current and accurate fuels products that are used updated on an annual basis and used every year for wildfire response and natural resource management. I thought it'd be good to briefly introduce some terms and concepts. We hear a lot about artificial intelligence lately, and that's really a general term for a computer function designed to mimic human capabilities, human intelligence. It's pretty broad. You're not saying a whole lot when you say artificial intelligence. You kind of need to, what human intelligence are you trying to mimic? What are you trying to do? What information do you have? And is it any good? So a subset of artificial intelligence is machine learning, and that's where you actually use computer algorithms to learn from data. So it's being trained. And this is what LANDFIRE has used since its inception. 20 years ago when it began, it was using machine learning to model vegetation, and it's what we're currently using today. We are starting to dabble in neural nets, which uses artificial neurons. It's a more sophisticated subset of machine learning, and we do hope to explore the possibilities of using deep learning as well in the future. But those models do require a lot of data, and we're working on building the data sets that could support those types of models. So we're going to be kind of hovering in that machine learning today, but that's kind of where this topic fits in with some of the terms getting passed around a lot in conversation these days. So machine learning, there's two main types. There's supervised learning and unsupervised learning. So this supervised learning, you're going to actually have labeled training data, and it's going to be based on, therefore, both the input and the output data. Unsupervised learning uses unlabeled training data, so it's going to be limited to just kind of forming groups and clusters and similarities, and then trying to pull out patterns that way. We're going to be looking mainly at supervised learning because our training data are all labeled. And there's two types of supervised learning. There's classification and then regression. We use both for different types of data. Classification is for categorical data. So think vegetation type. We also model dominant lifeform, dominant vegetation, and that's a category as well. So that uses classification. And then there's regression, and that's for continuous variables. So think vegetation cover and height. Those are going to be regression models. So that this was just a helpful way to lay out, we're looking at machine learning, the different types, and what we're dealing with on LANDFIRE. And it's also emphasizes the importance of why we spend so much time trying to get really accurate training data. Like the ecosystem type labels for the plots or the cover and height measurements from field plots or Lidar. It's because it's, this type of learning is dependent on the input data. You've heard the phrase garbage in, garbage out. And so we want want it to be, treasures in, treasures out, I suppose. So we want the highest quality data going into the model, and that's going to give us high quality, accurate data coming out, result in, the highest quality products possible. All right. So I have some schematics coming up here. This first one is really the general workflow for how we use machine learning in LANDFIRE to model vegetation. We start with our predictor layers. So sometimes you might hear these called independent variables. And we have satellite image composites as our primary predictor variables. So I just have all the bands shown here. Blue, green, red, near infrared, shortwave infrared. There's 2 of those. So that makes a 6-band image composite. And then the values for those pixels are made by looking at all the Landsat Sentinel scenes in a given date range. It stacks them up and then finds a percentile. So we can pick whatever percentile we want of that stack of reflectance values. We often use the 50th percentile because it gives us the average. But we also look at like the 15th percentile or the 90th percentile. So that forms the basis for our predictor variables. Now for our model, we need our response variable. Sometimes you might hear this called a dependent variable. So it's the idea is that this variable is going to be determined in response to these predictor variables that we're putting in. So these are our training samples. I guess these are called a few different things, but we store this information in the LFRDB, the LANDFIRE Reference Database. So it's going to be field plots, and that's what it's shown here. These are, they're geolocated, they're spatial plots that we have high confidence in what's going on there. We have information from the field. Usually it's, it started off as field plots. Now we're looking at Lidar. What kind of information can we get from Lidar to say this is what the vegetation is like here? And we have some other methods that we are exploring too, looking at a consensus map and sampling on that, sort of a convergence of evidence from other maps. It's becoming more common to build up your number of training points so you can support those deep learning models. And then we're analysts, so we can't help ourselves from going in and checking things out with aerial photos and street view and whatnot. And so sometimes we do put in plots from just that desktop review. So those are the 2 components of our model. And what we need to do is extract all the values on those predictor variables and associate that with each of our training points so that we can say, all right, for this point, if we know the tree cover looks like this, what does the reflectance value look for in each of our different bands? And that's how it's building those associations and relationships. So once we have that, we can go ahead and build our model. And you know, as we talked about before, we're using machine learning. So this is an algorithm. There's a lot of different algorithms out there. We've used, you know, things like C5, Cubist in the past. You've heard of maybe random forest. It's a really common one. Now people are using neural nets and deep learning, and that can be substituted for this step as well. It's doing the same function. It's building predictions. And once you have that, the final step is to extrapolate out for all of those pixels in your predictor variables. You can now predict what your response variable is going to be. And that's how we get our maps. So we start with points in space, and we end up with a prediction for every pixel in our map. So, you know, it kind of seems like magic sometimes, and it really is. It's pretty incredible what we're able to do. And, you know, our challenge is to take that information and put it all together into something that can be usable for creating fuels products and for other applications. So that's what I am going to explain in the following slides here. So let's take that framework and look at one of our specific models on LANDFIRE. One of the first things we do in the vegetation modeling process is label each pixel to the dominant life form, tree, shrub, or herb. So that's what we're going to do here. We start with various, what used to be Landsat, it's now Harmonized Landsat Sentinel image composites. We break it out into seasons throughout the year so that we can account for that, you know, seasonal variability, leaf-on conditions, spring green-up conditions, to really inform that model what the vegetation is like through those reflectance values. We also use an NDVI image composite. So for dominant life form, our training samples are going to come from a variety of sources. We have this information in the LFRDB for our field plots. We label each of the points that have enough information to an ecological system, and then that is crosswalked, you know, via a lookup to the dominant life form. So if it was labeled in a certain forest type, now that is a tree plot. So this is a pretty simple model. That's why I started explaining this one. We just have 3 variables. So our points are going to either be tree, shrub, or herb, and then it's going to associate that with all of our input variables through this process where we extract the values, merge that all together into a model file, and now we have everything we need to feed it into our gears there that crunch away our machine learning model. So that runs, and then we're able to map the dominant life form for every pixel. So this is a categorical model. So we're using a classification tree, and as you can see there, it's mapped out, you know, the trees versus the shrubs versus the herbaceous. So we define tree life form as, you know, a pixel that has over 10% tree cover. And if it doesn't have that, and it has over 10% shrub cover, then it's a shrub, then it's a pixel that's the dominant life form is shrub. If it doesn't have 10% tree or 10% shrub, and it has over 10% herbaceous cover, then it is herbaceous. And, you know, if it's barren or sparse, we deal with that later through a different process. So now we have the backbone for our vegetation maps. We have the dominant life form for each pixel. So now we can build out our cover, height, and type maps accordingly. So if we have a pixel that's tree dominant life form, we'll pick our tree type from the models. We'll pick our tree cover and tree height. So we'll look at those next here. I started simple and things are going to get a little bit more complex. So vegetation cover and height modeling, it uses the same set of variables. I included a new one here, tasseled cap. So on each of our seasonal image composites, we do calculate the tasseled cap index, which is really helpful for informing these vegetation models. And then we also have that NDVI composite. We have our training samples. Here we rely heavily on our field plots because this isn't something we can see from desktop or rely on a lot of other information because it's pretty difficult to get correct in other maps. So we're not referencing other maps here. We're going straight to our field plots. There's fewer of them, but they're high quality this way. And we have in the past used Lidar to inform these models, and we're currently working on further developing that process to use 3-depth airborne Lidar to calculate tree canopy cover and height. And that really will open up a whole new world. We're talking millions of training points that we can use to support neural nets, hopefully soon deep learning models that can really increase the quality of these products, increase, the accuracy is what we're really after. So we do the same process. We associate those training points with the reflectance values in those various satellite bands. Again, feed it into our machine learning model. This is going to be a classification. So we're using Cubist. Random Forest does this too. There's others, XGBoost, and then of course neural nets do this as well. And we're testing some of those. And finally, we extrapolate that out. So we do this 6 different times. We do it for tree, shrub, herb cover, and then tree, shrub, herb height. And we are able to extrapolate every pixel to each of those 6 map outputs. So now we have that, and now we need to merge it with our lifeform mask that we created before. So if the pixel is dominated by shrub, according to our lifeform mask, we're going to bring through the shrub cover and the shrub height to produce our modeled cover and height. And this is the final step for the modeling piece, and then we have to create a final map. So we do that by adding in our barren sparse, the water, snow ice, agriculture, developed, and roads. And I stack them up in order of priority. So if a source says roads, then we trump everything else, and likewise going down that list. These each, they come from different sources, or we create them ourselves. We spend a lot of time getting a really good water map that is put in here in this step, and we spend a lot of time getting a really good barren sparse mask, and that's a separate process. Every year we update agriculture because there's a new cropland data layer every year, and we update developed as much as we can. We use NLCD for that, and also building footprints to identify burnable and non-burnable developed lands. And then roads we are getting from NLCD as well, but we're looking at other sources for roads. And then that gives us our final EVC and EVH maps. All right, and the final piece in all of this is vegetation type. That one is the most complex. That's why it's here at the end. So we have the same image composites, but we also include topography, elevation, slope, aspect, and gradients, climate gradients, so precipitation, and then average, minimum, and maximum temperature. So that's really important for separating different ecological systems that occur in specific locations. North slope versus south. It's going to require certain level of moisture and temp range throughout the year to support specific species. So that's why we include those there. They don't necessarily always help with cover and height modeling, but they might, as those models continue to get more sophisticated and develop. So then we have our training samples, and that is going to be based on field plots, and we label those field plots to an ecological systems category based on the species there or other information tied to it that we can label with expert opinion. So this is a really highly technical and important step. We have hundreds of ecological systems, so identifying which one these plots fall into is not always clear, and we have to do it often in an automated way because we're dealing with tens of thousands of plots. So it's a monumental task, and but we get it done, and we do a pretty good job doing it. We get support from NatureServe to with their regional experts to help with that, because no one person has all the knowledge needed to do this step. So same thing, we extract all of those layers and associate those to our training samples, build our machine learning model. This is similar to lifeform. It's a classification, it's categorical data. And we get a lot of different models out of this because we have to separate out the different types and bring them together in the end. So we start our bases, we pull out all the non-riparian, non-alpine types and model them together with according to dominant life form. And then we take all the riparian or wetland types and model them together according to their dominant life form. And we do the same for alpine types. And then we have barren and sparse types as well that we have to model together in a separate model. And then it seems like every geography has a handful of difficult types that just don't behave in this sort of standard process that we have to break out and handle separately. And again, that all gets merged through that same lifeform mask. So now we have one layer for each of these different sort of categories of, or I guess groups of ecological systems. And then those get sent through a few different masks. So where do we put the riparian types? Well, we put them where the riparian mask says they go. And that riparian mask is created through a separate modeling process to identify wetland and riparian areas. We have that same barren and sparse mask that we saw before is used to constrain where our barren and sparse ecological systems fall. We have an alpine mask that was created to zone in on the alpine zone, and that's used for our alpine types. And then for the difficult types, they often have specific soils, or maybe there's a different layer out there that's helpful for constraining where that type occurs. And so that's all put together into our final model type layer. And then in the same way, we bring in all those non-vegetation types to create our final EVT map. So that's it for the crazy graphics. I have one final slide here just to show where we're at in evolution of LANDFIRE and how we're creating these vegetation products. So LANDFIRE started with 2001 base map, and that used this process, machine learning, to create those maps, and that was updated to account for disturbances in subsequent, biannual updates using rule sets until 2016. This machine learning vegetation modeling process was used again to remap all pixels. And the following two updates use that same rule sets process, but then we wanted to try to incorporate some of this modeling into an update process. And we did that for LF 2023, where we generated these models according to 2023 imagery and brought that through in pixels that were disturbed in the last 20 years as a way to get things trued up for current ground conditions where there's so much change that it's difficult to get it accurate with rule sets. And then now for LF 2024, we're using that same rule sets process, and then we'll see where we go from there. But I guess the final piece of this is that, this is being used to create our fuels products. So, that's the important connection there at the end we don't want to forget about. That is all I have for today.
So, what are you the most excited about as you think about technological advances that might be on the horizon or in the works as you think about applying them to updating LANDFIRE's product suite? And are there LANDFIRE layers or products that might be impacted more than others? If so, which ones?
Yeah, there's a lot of advancements with artificial intelligence, and I'm excited to see how it improves our existing products and also how we, it might be result in a whole different, I guess, framework for creating fuels products. So I'm excited about just creating better vegetation data, creating better fuels products. And then which products would be impacted more than others? I think all of our products, have the potential to benefit from technological advancements, artificial intelligence. Just because vegetation is kind of used machine learning the most, I don't think that necessarily means they're going to, be the main area that sees change in the future.
They're curious, how do you handle mixed pixels when modeling dominant life forms? Thank you
Yeah,
for
it's
answering
just
that.
that 30. Yeah, it's that 30 by 30 meter pixel. It's just a strict rule. If there's more than 10% tree cover, whether it's a half of the pixel, if it's on a border of a field in a forest or something, it's still, even if there's 15% forest and 85% farm field, well, in that case, it would be, I guess that's a different land cover. I'd say grassland, then it gets categorized as tree. But in the modeling process, if the grassland signal is really strong, even if the model's trained that way, it can sometimes get trued up in the end, I should say. But that's how we handle mixed pixels.
Michaela asks, can you speak more about the differences in the published datasets from 2016 to the more recent datasets?
There's two differences. The agriculture and developed are getting updated in each update. So that take the most recent agriculture sources and each updates to our sources of data for developed and gets those current. And then our disturbed areas are going to be transitioned forward. So if there was a recent disturbance event that, like a fire or a logging, then that would be reflected in the data. And those transition rules also account for regrowth. So for example, the cover might increase somewhat, depending on the type of vegetation there over time. Other than that, the pixels are going to be unchanged. They're going to be the same as what they were modeled as in 2016.
Sam asks, what's the future of updates, especially for this existing vegetation type? Will you use modeling or rule sets or both? Which is more accurate? And can these data sets produced after 2016 be compared?
Yeah, that's a good question. We actually don't update EVT with rule sets right now. For example, if you have a forest that gets logged, well, it's still a forest, so we leave the EVT as is, even though there's no trees there yet. We are assuming they're going to grow back, or that it, still has the potential to support the trees. Um, it's pretty, it's difficult to map with rule sets, so that's why we rely on the modeling. It's a little more realistic to do this with cover and height. And can the data sets produced after 2016 be compared? Yeah, they definitely can, just because of what I mentioned, how they were not necessarily changing. Like if a forest was logged, we're not changing it to a grassland type. Is how we're doing it right now. So I hope that answers that. Good question. I wonder those things myself too.
Iris asks, can you elaborate on garbage in, garbage out? Currently collecting information about user needs for high quality Earth observation data for important work like yours.
Yeah, we're constantly on the lookout for the highest quality data that we can get that works for these types of models. That's why we're looking at Lidar specifically for tree canopy cover and height, because there is a lot more of it than, because it's on flights rather than what we're limited to get to on the ground. And it's not something that can be subject to just field and personnel bias or differences in sampling methods. It's usually a standard data type that we're really excited about. Not only getting tree canopy cover and height, but hopefully in the future some more information on the canopy that could help with the fuels metrics like canopy base height and bulk density. But yeah, if you have more specifics on that question.
Yeah, thanks, Daryn. Just noticed that you guys use HLS and was wondering why that's a main input for your model.
Oh yeah, good point. We used to just use Landsat. We use HLS now just because there's so many more observations, and it results in more accurate image composites, or just with all those observations, the more that we have, the more reliable the image composite is going to be. So for a given pixel, before we might have 3 observations during a given date range. With HLS, we might have 12. And so it just increases our confidence of what the reflectance value is for that area, because all sorts of different things happen on different days of observation with the atmosphere and clouds and other artifacts that get in there.
And HLS stands for what, Daryn?
Yeah, Harmonized Landsat Sentinel. So Sentinel is 10 meter, and they, I believe, there's Sentinel, different types of Sentinel, but it's basically a merge of those two satellite data sets, and it's to 30 meters. So imagine, Landsat is revisiting a pixel. How often now? It's supposed to be every 8 days, I think, because Landsat 8 is every 16 or so. This is I don't geek out too much about this stuff, but so we have 2 Landsats up there, so that's a revisit. Each one's 16, so both of them is 8 days. And you include Sentinel in there, it can be every other day you're getting observations. So that's why we moved to using HLS.
Brett Williams asks, Have you explored using other remote sensing techniques for training data aside from LiDAR, such as high resolution NAPE imagery or other sources?
Yeah, we've heard of other folks doing that, but we haven't looked specifically at NAPE yet. It's difficult to, it's heavy, and then it's hard to get wall to wall. So that's kind of the two main reasons we haven't gone there yet. I know LiDAR is heavy, but we process it so that it's usable for us. But yeah, it's definitely a lot of researchers are doing it for study sites, and we just haven't found a way to sort of scale up with it. But LiDAR is something that's can give us the training data. So that's kind of the important part, and what I was trying to show in those slides is that the LiDAR we can have just a subsample of the map covered by LiDAR, and then we can extrapolate out with that machine learning. With the high res, it's hard we'd have to train, and some people do this, you'd have to have field data or something in that high res image to basically classify the high res image. And then you use that as training data to extrapolate out. So it's quite a bit more complicated, but it can be really good.
Hey, Daryn, Randy here. Thanks so much. It still blows me away what you guys do, whether they're 9 billion pixels in the lower 48, something like that. So incredible. One thing that caught my eye was the difficult types on the EVT, and that just made me wonder, in addition to us making sure that we can get you all the plot data that we can, all the good plot data, are there other ways we can help you? For example, with some of those difficult types, can we help? Do you have those processes in place? Like, how can we help you guys in a way that's efficient? I know like sending you 1 billion pixels with ideas probably isn't great. How can we best help?
Yeah, I appreciate that, Randy. I'm feeling the love. Yeah, it's just you start modeling and things just aren't working and you're like, boy, that's not looking so good. Maybe it's a type that occurs on sandy soils, but if you include soils into the model, it creates artifacts usually, or it can mess things up if you map everything with that as a predictor layer. So we often just use the soils as a mask to say, hey, this is where this type can occur, otherwise that type shouldn't be included in the model type thing. And then there's actually some types that we just can't model very well at all, like the remnant prairies or things like that we actually go in and just digitize by hand. I don't know if this is what you're looking for, but I think just having a smart classification, having a classification that is separating the veg out in the best way for fuels, and that is also mappable. Thinking about some of our types, they might be good for, certain ecological applications, but if we're not able to reliably map them, with these methods, maybe we should try doing something else. But if I think of something that you guys could specifically help with, I'll let you know. We had it was a fellow from the GAP program helped digitize some of these types the first go around, and keep an eye out for any predictor layers. We're watching what's going on with soils. There was the G-Surgo and then Polaris soils. Neither one of those played nice with the modeling, other than being used as a mask. But yeah, if you hear of any new data sets, feel free to pass them along and we'll take a look.
Great, thanks. That's interesting. You mentioned soils. I was thinking about in our neck of the woods, the alkaline conifer hardwood swamps and the boreal acid peatland kind of do this. So getting good pH data would be amazing, but I don't think there's anything out there that teases that out. But that's an example I was thinking of that probably doesn't help.
The imagery can do okay on those types. If the signature in the imagery is clear enough. And it often is with those peatlands.
I'll jump in.
Sure.
Thanks so much, Daryn. That was a really great presentation. I learned a lot. I especially enjoyed your little slide at the beginning about AI and kind of putting that in context and where LANDFIRE's methodology falls on that AI spectrum. But what I'm really wondering about is there was a LANDFIRE mapper that used to say we live or die by the plot. And as your presentation kind of showed, everything's tied to that plot classification. Well, a lot of it, not everything, but so where could you just give us a broad overview of where you think we have really robust plot information, either geographically or certain veg types, and maybe where we're lacking information on the ground in plots?
We often have, like those desktop plots I mentioned, those are often places where people don't easily get, like alpine, barren lands. Field crews are just not going there to collect data. So, like the sagebrush, we have a lot of data for that. Although we do have a lot of different sagebrush types, and they often get confused in the plot labeling. For example, like there's a semi-desert sagebrush type that has sagebrush, but it has a smaller percentage of herbaceous cover in between. Well, there's a lot of rangeland that gets pretty beat up, certain years, and we had a lot of this semi-desert sagebrush type where it probably wasn't really that type. It was just overgrazed. So that's just one example of the complex or the challenges. But a lot of these highly studied systems we have pretty good data on, but it's the places where aren't being studied or are difficult to get to on the ground. And again, I hate to take it back to the classification, but sometimes that's the most important piece because, for example, like Douglas fir, there's a dry music and then a music Douglas fir type, and telling those two apart at the plot level is actually really difficult. So it almost has more of a factor with just topo position and stuff like that. So I think more of that in the labeling process would help, or just reviewing some of these ones that are tricky to separate with the plots. Yeah, that's a really good question. Yeah, sometimes I wonder if we should base the classification on what we have in the plots, because sometimes we're splitting stuff out in the classification that we just don't have that information at the field plot level, or not enough of it. So it's kind of tied together that way. And then it's interesting, you see a map of where we have plots, and sometimes you can see state boundaries because some states just provide so much more data than other states. So it's a lot to expect, of getting all this information on the ground, and that's why we're looking at, there's stuff like hyperspectral data now that can get at species from the air.
Bill asks, what type of predictions are made by season as far as wildfire goes?
Yeah, the seasonal image composites are used to inform what vegetation is there, because if we use imagery for the whole year and try to get percentiles off of that, it's going to wash out any sort of phenology, especially if there's leaf on, leaf off conditions. So that's why we split the composites into seasons, is to get better information to our models. But as far as like different predictions for different seasons for wildfire, we do have a seasonal fuels products that are, there's 4 of them: early spring, summer, and fall, that adjusts our fuels products, our fire behavior fuel model product, based on NDVI for imagery for that season. Think about annual grasses, and they'll green up in response to precipitation and then pose a fuel hazard. So fire hazard. That's why we do that, to try to track that intra-seasonal changes. Hope that helps.
Laura has a question. Has Landfire considered using the eBird or Christmas bird count approach to collecting field plot data to enhance the training or validation data?
Yeah, like citizen science, I think, is another term for that. Yeah, definitely. I think it's got potential. Then you introduce some of the challenge I talked about with different ways of measuring tree cover, or canopy cover, canopy height, relying on the most reliable way to do that for us is actually to measure the diameter of the trees, because that is one of the more empirical ways of doing it, rather than just looking up and estimating. And then we have all these different ecosystems, but I definitely think it could work for stuff like lifeform. If people could just put in what the different species are. We've definitely thought about it, but we just haven't gone there.